We are on to the we're on to the nuclear chemistry chapter. And again, the first little part there was a recorded lecture, so make sure you do watch it as you are responsible for it. A couple of things that was in that lecture, basically last time. Nuclear chemistry is very different than regular sort of chemistry, in the sense that in a chemical reaction, basically all it deals with is electrons, and it deals with breaking bonds and making bonds. And because of that, we never touch anything in the nucleus. And that is why, for example, when we do balance a regular equation, we always just basically balance it by doing the coefficients. And that's because we do have in a normal chemical reaction conservation of the elements, because as you hopefully know, the atomic number, which is the number of protons, determines what element you're dealing with. And since we don't do anything inside the nucleus in a normal chemical reaction, we really don't change any elements. And that's like completely different in sort of nuclear reactions. And in nuclear reactions, it's really all about kind of playing with what's in the nucleus. Sometimes you change protons to neutrons, neutrons to protons, and so forth. So what ends up happening in nuclear reactions is it's all about those sort of protons and neutrons that are in the nucleus. And because of that, we actually do not have sort of the same elements that we start with. So we don't really have the conservation of elements that we see in a chemical reaction, in a nuclear reaction. So really, what we sort of start with will definitely change to different things here on sort of the product side. And because of that, and because we're playing with basically what's in the nucleus, it also involves a lot more energy than a traditional chemical reaction. So I think we'll see it again, but probably also mentioned in that lecture, your exothermic sort of chemical reaction, maybe will give off like times 10 to the 6 sort of joules of energy. A nuclear reaction will give off like twice as much or even 3 times as much energy, again, because you're playing basically with what's in the nucleus. As a reminder, right, when we talk about radioactive sort of isotopes, isotopes in general are written with the symbol, and very commonly, top left is the mass number, which is sometimes abbreviated with an A. Bottom left there is the atomic number, which is sometimes abbreviated with a Z. Again, the atomic number is the number of protons there are in an atom. Remember that that is actually the definition of atomic number. It is actually only a number of protons. It will also tell you the number of electrons if it is neutral, but the actual definition of atomic number is really just the protons. The mass number is the number of protons plus the number of neutrons. And by using both of those things together, if you take the mass number and you minus the atomic number from it, you will end up with the number of neutrons in that case. So that's also very common. A reminder as well that it is only the atomic number that can be found on the periodic table. Also a reminder that the bottom number is not the mass number, that is the atomic mass. And when you calculate anything like mass number, atomic number, number of protons, electrons, and neutrons, they all should be positive whole numbers. And obviously, if you look on the periodic table, all those numbers on the bottom are definitely not whole numbers. And again, they are not the mass numbers. So if you have to figure out the mass number, you will be given enough information to sort of calculate it, but definitely only the atomic number is found on the periodic table. Sometimes isotopes are written like this: 64 copper dash 64. The 64, the number that you see after the dash, is the mass number, and that is again typically how that's written. Once again, you can't go to the periodic table and get the atomic number for any element that you may need. Now, because of this, all elements do have protons, electrons, and neutrons, except for hydrogen that has a proton and an electron. It does not have a neutron. But because of this sort of difference in what's happening with the nucleus, when we balance nuclear equations, we basically, because we do not have conservation of elements, basically there's two things that you want to make sure is done when it's all said and done. When you add up all the mass numbers, which are the numbers up on top on the left-hand side, it does need to equal all of the mass numbers on the right-hand side of the arrow. And same thing with atomic numbers. If you add up all the atomic numbers on the left-hand side of the arrow, it should match all the atomic numbers on the right-hand side. So if you're given a nuclear equation, something is missing, probably the atomic number is a good place to start with, as you could just simply use the periodic table and figure out what element's missing. And then you could also take care of the mass number. A reminder that if you do have a coefficient in front of something in that equation, you do have to multiply that coefficient by the mass number and the atomic number as well to take advantage of that. Now, what happens in nuclear reactions or equations is there's a lot of nuclear sort of particles that are sometimes emitted or sort of captured. Some of the particles, we have alpha particles, which is a 4 and a 2, or you can use 4 and a 2 helium as the symbol for an alpha particle. Again, either one is fine. We also have beta particles, which are really negatively charged electrons there. And you can use the electron symbol, or you can use the beta symbol as well. We also have gamma rays, which is basically just pure energy. So we just use sort of the gamma symbol for it. There's also positrons. Positrons are basically like beta particles or electrons, except that they're more positive. So that's a +1 type of situation. Or again, you could use the beta symbol +1 as well. So um, definitely there is a difference between these two. And usually there is some type of distinction that's made in the problem so you know which one they're talking about. I would say if you just simply see a beta symbol, you could probably 99 times out of 100 assume it's probably the beta symbol. If they wanted the positron symbol, they would do something like obviously include the numbers there, or maybe they might just put a plus in front of it as well to sort of indicate that you're talking about sort of the positron in that situation. Other sort of symbols and stuff that we see, our friend the neutron, right, is this abbreviated like so. Also our proton, which is either with a P or a hydrogen for a proton. Again, that is another common sort of symbol. Now, when we talk about sort of nuclear equations and reactions, if something is emitted, that particle is usually on the product side. If that sort of says it goes through beta decay, then again, that beta particle will end up on the product side. If something is captured or bombarded, that particle would end up usually on the reactant side. So, for example, an electron capture, if you were writing an equation for it, because of this, you would put the electron on the reactant side. If you had like alpha emission, that would put the alpha particle on the product side. So again, sometimes in the balancing of these nuclear equations, you're given everything in words, and you just want to make sure everybody gets to sort of the correct side there. Now, what else is going on here that we talked about? We talked about stability. And one of the common ways to look at stability is the N to Z ratio. And that basically is the neutrons to proton ratio. And there is sort of an acceptable ratio depending on your element. And that acceptable ratio is sort of what is sometimes referred to as the valley of stability or the belt of stability. And if you find your kind of neutron to proton ratio either too high or too low from that sort of stable belt, the isotope there will go under a decay process to try to become more stable. If you're too high, what will typically happen is it will go through a beta decay. And that will then move it kind of lower the ratio and bring it closer to the belt of stability. If you are too low, it will do one of two things. It will either do an electron capture or a positron emission. And the result of that is it'll kind of bring up the ratio closer to the belt of stability. Now, you may be wondering why you have maybe two options here. And the reason really is they will give you the same product. So if you do an electron capture or a positron emission, you will end up really with the same product regardless of which one you do. An alpha decay can also be used for low, but we're not going to use it, as I probably said in that lecture, because it's not really efficient. So if the ratio is too low, it'll be either the electron capture or the positron emission. For example, if you had like lithium 7 or something like that. If I had lithium 7 here and it went through an electron capture, we would end up with, again, we need to balance out the top. So that is 7. On the bottom, that is 3 and minus 1, basically, which is 2. And that would get me to helium in this case. And that would balance me out. Again, I got 7 on the top and 2 on the bottom there. And I got 7 on the top and 2 on the bottom. And that would be our balance equation. If we did lithium here with a positron emission, again, the positron particle would be on the product side. Here I have 3 on the bottom and 1 on the right. Missing is 2, 7 on the left, 0 on the right. Missing is 7. I go to periodic table. Again, number 2 is helium in this case. So as you can see, either one of these will get you basically the same product. So you do have that sort of option. Will it give you a perfect sort of ratio when it's all said and done? The answer is it will not in a lot of cases, but it should kind of improve the ratio and move it sort of in the correct direction towards the valley of stability. How do you know what is a good ratio or not? It does depend on the atomic number. So, for example, if your atomic number is between 1 and 20, an acceptable stable ratio of 1 for N to Z. If you're like 20 to 40, it's like 1.25 and so forth. So it does depend on sort of the atomic number as to whether it's going to be too high or too low. As I mentioned in that lecture, we typically will do a pretty hard cutoff on those. So it is either that number of 1 or it's too high or too low. As I might have mentioned in that lecture as well, usually sometimes it's sort of a grayish area because, for example, this one is 1 through 20, next one's 20 through 40, so it kind of ends and begins on the same number. So sometimes there's sort of a grayish area in terms of that. So I'll try not to give you one that's on the grayish area, and we'll use the N to Z ratio there as a really hard cutoff so you know what is going on. Last thing I think that was in that lecture, go here, was this right here, a decay series. And a decay series is really a pattern of decay processes that occur until something basically becomes fairly stable. So for example, in this case here, we're starting with uranium 238. And again, I could go to periodic table and find uranium, which is number 92. Now let's just say I'm not going to do the whole thing here, but we'll just kind of do these 4 steps in the process here. And let's just say we started with this and it went through an alpha, a beta, and an alpha decay. Now, there's a couple different ways you could kind of do that. One way is basically just to write the individual balanced nuclear equations. So, for example, what I would do is take my 238 and my uranium and my 92. Again, the first step is going to be an alpha emission, which tells me my alpha particle will be on the product side. Once again, 92 there and 2. If I subtract that, the difference is 90. And that's really the missing element here. I go to periodic table, find number 90, which is TH. I got 4 on the right, 238 on the left, gives me 234. This would be sort of the first decay process. Next, it's going to go through a beta decay. And what I would use is the results of the first step here, 234.90. And now again, a beta decay means we're going to go product side with our beta symbol. Again, you can use the electron here. This is 90 and minus 1, which means we actually have to go one more in this case. And that will give me 91 and minus 1 is 90 on the right-hand side. The number 91 on the periodic table is PA. Top, we got 234 and 0. So we'll end up at 234. And that would be the second step. Then we'll take what is produced here, 234, 91 PA. Also go through a beta decay, which again can use the E or the beta symbol here. Once again, in this case, we actually have to go up 1 to 92 on the right. 92 and minus 1 is equal to 91. And again, going to periodic table, number 92 is back to uranium and 234. And lastly, in this just short little process here, 234 uranium, 92 also going to go through here an alpha decay. And missing number 92 and 9 and 2 is 90. Again, back to the periodic table, TH, 234 and 4. Going to need 230 there. So this is one way that you could do a decay series, which is really just writing the balanced nuclear equations or for each thing. Whatever you produce on the first step becomes your starting on the second. And then obviously what you produce there becomes your starting and so forth. And you can continue that process really until it gets all stable. Now, if you are dealing with something where it's really just alpha and beta decays that are happening, and you're really maybe just interested in what you'll get at the end of the process, you can kind of take a more mathematical approach. For every alpha decay that it goes through, you're going to subtract 4 from the top number, the mass number, and you're going to subtract 2 from the atomic number. And for every beta decay it goes through, you're actually going to add 1 to the bottom number. So to the atomic number here, we would add. So in this case, we had 2 alpha decays. So that means minus 4 and minus 4 up on top, minus 2 and minus 2 on the bottom. We had 2 beta decays. That means on the bottom, plus 1, plus 1. So if we take a look at what we started with originally, we had basically 238 up on top, minus 4, minus 4. That gives me a 230 on top. On the bottom there, we started with 92, minus 2, minus 2, plus 1, plus 1. So that's 90, that's 88, 89, and 90. And again, that gives us basically where we ended up at. So again, if you're not maybe interested in kind of everybody along the way and you just want to kind of get to what you would get at the end of the decay series, you can kind of do more of a mathematical approach. Any questions on any of that stuff there that was in that recorded lecture? All right, then we're going to pick up because I think this is where it left off. So the next thing we're going to actually talk about in terms of radioactive decay is kinetics. And all radioactive decay follows first order kinetics. So if you remember your kinetics lectures from 200A, there's first order, second order, zero order. But all radioactive decay follows first order kinetics. And really, first order kinetics deals with basically a couple of important things. First off, we have sort of the integrated rate law, which is sometimes written like this, the natural log of A equals the natural log of A naught minus KT. This is sort of your final concentration. This is your initial concentration. This in kinetics is your decay constant. Here in sort of nuclear chemistry, I'm sorry, and that's your rate constant in regular chemical kinetics. Here they call it the decay constant. And T here, it's actually time. So that is actually time in this case. Now, this integrated rate law can be used a little bit differently than maybe you remember in 200A. Now, in typical chemical kinetics, we oftentimes deal with molarity because we're looking at solutions and stuff like that. And in this case of radioactive decay, these guys here, although they are sort of thought of as concentrations, they could actually be concentrations, but they really could be any type of unit. For example, they could be grams and grams, they could be milligrams and milligrams on each side. They could actually be rates of radioactive decay, like counts per minute per gram of carbon. So it could be any type of unit really that you want to put in there. They just need to be obviously the same unit for both A and A naught for everything to cancel out correctly. The other thing that you usually want to be also very careful of as a reminder in kinetics is these two guys here. And for example, in first order kinetics, the rate constant, or in this case, the decay constant, typically will have units of reciprocal seconds, are really 1 over some unit of time. It doesn't necessarily always has to be seconds, but that is a very common unit, but it can be anything. And that's really how you know it's a first order sort of kinetics problem. When you look at the rate constant, you do see reciprocal unit of time, basically 1 over minutes, seconds, hours, days, whatever it may be. Now, with that being said, you do have to be very careful of the unit of time that you have in the decay constant, and obviously the unit of time that is the time part of it. You may have, for example, weeks in one and days in the other, or maybe years and days or something like that. So you do have to do sometimes some conversions there to make sure that they do end up in the same units. Otherwise, you will be off. Obviously, half-life, like we kind of talked about today, for first order kinetics is the natural log of 2 divided by the decay constant. If you've done the natural log of 2 on your calculator, that's going to pop you a 0.693 over the decay constant. Now, I would also say very, very common in these types of kinetics problems that deals with radioactive decay, we oftentimes will use the half-life equation and the integrated rate law together. So those two formulas are oftentimes used together. So very commonly, you may not be given the decay constant, but you will be given the half-life. So very, very common. We use the half-life equation to figure out the decay constant, and then you could kind of put that into this equation up here and solve really for what you're looking for. So very common. You do have to kind of use those kind of equations together. Now, since it's nuclear chemistry, they like to use their own symbols. So instead of A, for example, they will use N, which is a nuclide. And it's the same idea. Basically, natural log of N is equal to natural log of N naught. So that is your final, that's your initial minus KT. So sometimes they'll use their own symbols. In addition, instead of K for the decay constant, some older books and stuff will use lambda actually to represent the decay constant. So sometimes in nuclear chemistry, lambda is sort of used by nuclear chemists to represent the decay constant. Any questions on that there? Now, as you may be familiar with, there's also two graphs that are associated with first order kinetics. And by the way, if you take the integrated rate law there and rearrange it, natural log of A is equal to minus KT plus the natural log of A naught. That is the first order kinetics equation that deals with concentration and time, written in the form of a straight line. Y is equal to mx plus b, basically. Now, if you just graph the concentration of the nuclei versus time, you see this decline over time, which is kind of what your graph should have looked like today, probably, as you did it. Again, starting high and coming low. Now, very much in kinetics, they're all about kind of the best fit straight line type of situation. So if you rearrange it like I just mentioned there on the y, this is the natural log of the initial concentration. On the x there is the time, and that would yield you a straight line where the slope of this line would equal minus k, as that is a negatively sloping line, which would give you a negative number. The two negatives will turn your rate constant or your decay constant into a positive number. Any questions on that there? Now, in terms of half-lives, there is a variety of sort of half-lives that things can have. Some things can be very, very long, like you see there, uranium-238 is 5.5 times 10 to the 9 years, so none of us make probably any one half-life there. So it's a very, very long time. To something, for example, like radon-220, it's about 55.6 seconds. So every 55.6 seconds, half of it's going away. So it's very, very quick, basically degrading. Um, and obviously, we have things in between that could be days, hours, and so forth, depending on what you're using. Even isotopes of the same element may have different sort of half-lives. For example, I used to do research with copper or radioactive copper, and there was copper 64 that had like a half-life of like 13 hours, and copper 67 that had a half-life of 3 days. So they're very different, even though they're both the same sort of isotope and situations like that. Clearly, if you're using any type of radioactive sort of isotope for something like medicine or anything like that, obviously you would want a very short half-life. And a lot of things that we use for, say, nuclear power, like uranium, has a very, very long half-life. And again, that brings up issues of storage and what to do with that stuff for a long period of time. All right, so why don't you give this a go? If you have a 1.35 milligram sample of plutonium 236, what would be the mass that will remain after 5 years? The half-life of plutonium there is 2.86 years. So why don't you give it a go, see what you come up with. Okay, so let's take a look at it. So the nice thing about sort of this chapter is if it's nuclear chemistry, you know really what order kinetics is going to do. And what that basically means is you kind of already know the equations you should use, which is basically this one here. And again, you can use the regular kinetics equation. If you want to use the fancy letters, you can. You don't really need to. And our half-life equation that goes with it is natural log of 2 over k. So once again here, we're looking for a couple things. If you have a 1.35 milligram sample, so that's our initial sample there. Calculate how much will remain. So we are looking for this guy after 5 years, which would be our time. So if we just go to sort of our equation there, we're looking for this guy. We have this one. We have our time. We are missing our rate constant or decay constant, but we are given the half-life. So as I mentioned before, very common to use the half-life equation here to get to our decay constant. So that's what I'm going to do first. I'm going to rearrange the half-life equation to solve for the decay constant, which is k is equal to the natural log of 2 divided by the half-life. 86. How about a 0.242? Seems better there. 0.242 here. And let's see what that just does here. Probably makes it probably like the right answer, which would be good. Let's try that here. All right. Okay, so let's try this with the right numbers in there. Natural log of 1.35 minus our 0.242 times 5. That's going to give us here, that looks a little bit better, negative 0.9099. Again, E in both sides in this case. will get us 403. How's that? 0.403 milligrams. Thank you. Other questions on that there? All right, so let's take a look at another one here and see. All right. Radon 222 is a gas that's suspected of causing lung cancer. It's produced in uranium decay. Assuming no loss from leakage, if there's 10.24 grams of it in your house today, how much will be there in 5.4 weeks? The half-life of you radon there is 3.8 days. So see what you come up with there. Okay, so let's take a look again here. Try to do a better job this time. So we're going to roll with our same equation here. And our half-life equation. And in this particular case, we have initially 10.24 grams. We want to know how much will be there at the end. In this case, our time is 5.4 weeks, and our half-life is 3.8 days. So once again, if we kind of look at it, we are looking for that. We have that. We have that. Once again, like I said, very commonly here, we don't have the decay constant given to us, but we do have the half-life. We also can see, hopefully in terms of our time, we are going to have some unit issues. So you do have to convert, either the days to weeks or the weeks to days. It really doesn't matter which one you do. I think maybe I'll go days to weeks. Why not? So I'll convert my half-life here into weeks just to start out with. So again, everything will be in the same units. So there are 7 days, they say, in a week. And that's going to get us here a half-life of 0.54286 weeks. I again could use that here in my half-life equation to get to my decay constant. My K is equal to the natural log of 2 divided by my half-life. And put the right number in this time, 0.54286 weeks. And if I do that, natural log of 2 divided by 0.54286, going to give me a 1.2768. Again, reciprocal weeks in this case. Obviously, at this point, if you kept it in days, you'll have a different number because yours is in days, and then hopefully you converted that into days on that side. Putting it in here, natural log of A is equal to my natural log of 10.24 minus 1.2768 weeks, reciprocal weeks, and that's going to be times my 5.4 weeks in this case. Now that I did that conversion, everybody should cancel out okay. Cleaning up the right-hand side here, natural log of 10.24 minus 1.2768 times 5.4, going to get me a negative 4.5684. Natural log of A. Once again, I'm going to E both sides there. And we'll end up with a final concentration of 0.0104. The units here would be grams, just like our original as well. Any questions on that one there? Again, depending on rounding too, you might get a slightly different number, especially when you do kind of the inverse of natural log. Any questions on that one there? Okay. All right. Now, we could also use sort of what we've been doing to do some radioactive or radiocarbon dating, or really some radio dating. And we oftentimes could do that by, again, sort of following how much, for example, carbon 14 is left in it. You could also do uranium dating by figuring out how much uranium's left or how much lead is actually produced in this case. or really the ratio of these two guys that's left over sometimes is used. We use the same equations that we just used on the previous ones, except in this case, a lot of times you'll be solving for t, which is time to tell you how old something is. And we do have sometimes a different sort of unit. So, for example, here we have an ancient skull, gives 4.5, and this is actually a unit here of radioactive decay. So that is a unit of radioactive decay, and that is disintegrations per minute per gram of carbon. So the C here is not Celsius, it's actually carbon. And that's important here, that's per grams of carbon, because it will tell you that is the half-life that you want to use in this sort of situation here. So sometimes people think Celsius when they see the C a lot of times, but in this case it's per gram of carbon. And obviously with some other element you would want to use somebody else's obviously half-life, but here 5730 would be the half-life that you want to use because that is carbon. So if a living organism gives 15.3 disintegrations per minute per gram of carbon, how old is the skull? So why don't you take a few moments there and see what you come up with. We're going to roll with our same equations here, which is a pretty safe bet in nuclear chemistry here. It's going to be one of these guys here. All right, so in this particular case, we have an ancient skull and a living organism. So I'm going to say the ancient one is the final, 4.5. Again, disintegrations per minute per gram of carbon. Our initial, which would be living, 15.3 disintegrations per minute per gram of carbon. Also makes sense. Obviously, here it's living, so it's more radioactive, right? So it has a little bit more sort of counts per minute, if you will, or radioactive decay happening here than it does at the end. We want to know how old it is. So in this case, we are looking for time. And once again, if we kind of check off everything here, we have that, we have that. We're looking for time. So as we've seen previously, we do need to use the half-life here to get to the decay constant. And once again, a reminder that that is carbon, which is how we kind of know to use carbon's half-life here. So using carbon's half-life and rearranging the natural log of 2 divided by the half-life here gives us the natural log of 2 divided by 5730 years. And that's going to get us here 1.21 times 10, and 1, 2, 3, 4, minus 4. Again, reciprocal years in this case. Now we can put into our equation natural log of our final, which is 4.5, equals natural log of our initial, which is 15.3, minus our decay constant we just calculated. And we are going to solve for time here. In this case, it is going to end up in units of years, as that is what our decay constant's in. So natural log of 4.5 minus the natural log of 15.3. That's going to give me negative 1.2237 equals minus 1.21 times 10 to the minus 4 years and time. Again, basically, I took this guy and subtracted it to the other side. At this point, we're going to divide over, and we'll take that number and divide it by negative 1.21 to the negative 4. And that's going to get me a t that is equal to 10114 years. You guys can clean it up to about 3 sig figs if you like, which is about 101 00 years. Prefer that better there. Any questions on that one there? Yeah. It's about Yeah, so the way I remember it is living's like you're alive, so it's kind of like the beginning. And unfortunately, right, when we die, that's the end, right? So ancient, something that's old or, sort of ancient would be your final. You also know that really based on the radioactive decay here. So this guy is giving off a lot more sort of rates, if you will, of radioactive decay. So it's much more active, much more alive, if you will. This one is kind of slowing down and dying a little bit more. So it's giving off a lot less. So that kind of difference there in the numbers that you see on those is also a good way to remember it. Other questions? All right. That's what we just did, I think. Let's try one more here. An archaeologists have dated a civilization to 15,600 years ago. If a living sample gives you 20 counts per minute per gram of carbon, what would be the number of counts per minute per gram of carbon if you found a piece of rice on the site? So give it a go. Again, probably the same. All right, so let's take a look at this one here. We got natural log of A, natural log of A naught minus KT, well, half-life action. So in this case, we actually are given time, 15,600 years, a living sample. So again, as our conversation a second ago, that's going to be initial 20 counts, again, per minute per gram of carbon. And again, that's just again a unit of radioactive decay. As we talked about before, in sort of nuclear chemistry, you really could use any units you want in the concentration. They don't have to be necessarily molarity or anything like that. We're actually looking for what the counts per minute per gram of carbon would be at the end. And again, in this case, we are missing our decay constant. Since this is still per gram of carbon, we'll use our same half-life as we had in the previous problem there of 5730, and that will give us basically the same 1.21 half-life there, 5730 years. So again, going in there, we're going to get basically our same answer we had on the previous one. And that should be our 1.21 times 10 to the minus 4, I think it was. 1.21 times 10 to the minus 4. Again, reciprocal years. Here we have years, and again, for our time, we have years. So unit-wise, we're going to be okay on that. Putting it in, natural log of A equals our natural log of 20 minus our 1.21 times 10 to the minus 4 years, reciprocal years, times our 15,600 years. Here again, the years are going to cancel. We will end up with the same units as the first guy. Natural log of 20 minus 1.21 to the minus 4 times 15,600. Looks like we get a natural log of A is equal to 1.108132. Gonna E both sides there, and looks like we'll end up with 3.03. Once again, as I mentioned before, counts per minute per gram of carbon would be our units. This is our sort of older rice that was found there from a while back. It is given off less radioactive decay than obviously our living one. So again, you shouldn't end up with more than 20 in this situation. Otherwise, you're going in the wrong direction in this particular case. Any questions on that there? Yeah. Does uh yeah, so this is a unit of radioactive decay, and it's the units are basically how many counts per minute per gram of carbon. So that's all basically the units there is. It's basically counting every minute a gram of carbon, how many counts of radioactive decay is giving off, basically. Just like the other one, basically disintegrations per minute per gram of carbon. So for every minute, for every gram of carbon, basically how many disintegrations, basically how much radioactivity is being given off by that. So those units are similar to, for example, like if you use grams and grams like we did earlier, milligrams, milligrams, or even in regular kinetics, you could use molarity and molarity. So there's a little bit more when you talk about regular kinetics, usually it's like it has to be molarity that goes in there. But in like nuclear chemistry, it really can be any unit as long as they are the same on both sides for those two guys. Other questions? All right, I think it's good.